Hi, folks. Welcome back. Today, I want to take a look at this paper which talks about how we should be picking the design of our multi-agent systems. And I found this paper really interesting because it presents a lot of great empirical evidence for what kind of multi-agent architectures work well in what scenarios. So, of course, the background here is that as we're designing and implementing these agentic systems, we often try to break the system down into multiple agents collaborating and communicating with each other. There's planners, there's solvers, reviewers, etc. But the way we do it right now very often mimics the way human organizations are built. So you might have an agent for different personas, different roles, different functions, and so on. And so this is almost like skeuomorphic UI design back from the early days of the iPhone, where we're taking this entirely new medium, which is AI, and we're trying to impose human organizational structures on it. And that may or may not be the best strategy. And this paper tries to answer that question in an empirical way. If you look at human organizations, like the author says over here, they are sustained by motivation, identity, trust, employment, socialization, and so on. But AI systems have none of those motivations or constraint. They are held together by completely different things like prompts and memory and traces and context and so on. So that's what this paper looks at. Now, before we even get into how you pick a specific multi-agent architecture, one of the main ideas in this paper is that the mechanism connecting these agents is what the author calls contextual transaction cost, which is to say, if you have multiple agents communicating or collaborating with each other, how do they create and then share context with each other without losing coherence while still staying on task? And I thought this was such a great way to frame it because, as the author themselves say over here, it goes back to this very fundamental notion by an economist named Coase, Ronald Coase. And he put forth this very fundamental paper back in 1937, which talks about why do even companies and firms exist? Why would you form a company as opposed to just independently contracting a bunch of people to do a certain economic task? And the idea that Coase put forward back then was that the whole point of having a company is to lower transaction costs, in that it's much easier in terms of transaction costs to direct a set of employees than to direct a set of independent contractors. And so that idea comes through with agents as well, in that if you have a multi-agent system, there is some cost to them coordinating with each other in a fruitful manner. So keep that idea in the back of your mind as we go through the rest of this paper. All right, so the author sets up a nice empirical research testbed. They've created 8,000 synthetic knowledge world tasks and collected LLM traces for solving those tasks with various different kinds of multi-agent architectures, and then analyzing the traces and the success rate and efficiency of all those solutions with different architectures is the main set of results in this paper. So let's look at that next. So what different architectures did they look at? They looked at 7 different organizational forms. The simplest one, of course, was the single expert, where you just have one monolithic agent. Then you have some kind of a sequential pipeline where you still have specialization with each agent. Then you have your typical hierarchical multi-agent system where you have one manager at the top overseeing several sub-agents. You have this committee debate kind of structure, some kind of decentralized structure, and then what the author calls a blackboard memory form, where all the agents read and write from some commonly shared memory and context store And then lastly, you have this completely agent native way of organizing the system, which is an adaptive organization where the agent itself or the model itself decides the best kind of multi-agent structure to solve the given problem. And so you'll see this spans kind of all the common ways of architecting multi-agent systems. So, what did they find? The most important finding in this paper is that skeuomorphism does not work, or doesn't work well at least. What I mean is that if you make your multi-agent architecture in a way that imitates human organizations, you don't get great performance. That I would say is the central finding of this paper. And you can see it in this graph where you see efficiency plotted against all these different kinds of architectures. And efficiency here is a measure of the success or accuracy divided by the total cost. And you can see that the agent native ways of organizing your system come out at top. The two best performing methods were adaptive organization, where the model itself decides what kind of agents to decompose the problem into, and this blackboard memory system, where everyone reads and writes from this shared memory and context store. And if you look at all the structures that mimic human organizational structures, like having a single expert or a hierarchy committee or specialized roles or debating with a committee, they all perform much worse than the agent native structures. And you can see how big the gap is. Like the author says over here, the agent native forms are nearly 4x more efficient than the human imitated forms. So, what is the mechanism that explains this performance gap, the underlying mechanism? And it is contextual transaction cost. That's kind of the central idea of this paper. And how do they precisely define it? So it is a weighted sum of the token and latency cost, the cross-agent handoff, how much information you lose, how much semantic drift there is, how much you spend verifying the output of some previous agent, how much you spend looking at governance or whether all the constraints are adhered to. So there's a number of things that go into calculating transaction cost, but at an intuitive level, you can roughly understand it not just as how many tokens are spent, but then also how much cognitive effort the agents or the models have to do to make sure the handoffs and verification and semantic drift are properly kept under control. And there's a trade-off here, because if you have very small architectures or architectures with a small number of agents, like a single expert, you avoid context transaction costs, but then you give up on specialization. On the other hand, if you break down your problem too much, you really pay a lot in transaction costs, and you have a lot of handoffs, a lot of loss and semantic drift during those handoffs. The agent native ways, like using a blackboard or adaptive orchestration, seem to be hitting a sweet spot when it comes to contextual transaction costs. Because you have this shared context and memory, you don't have to keep handing off things, and everyone or every agent can work off of this shared understanding of the problem and the progress on the problem. The other big finding in the paper is trying to answer this question of, well, as you increase the number of agents, what happens to performance? And this is another pretty interesting finding. As you can see in this graph, it depends on your architecture. So if you just look at free text debate, it deteriorates as you increase the number of agents. Whereas some of these other methods, like having a structured blackboard, mostly are able to stay at the same efficiency as you increase the number of agents. But the idea here is that increasing the number of agents only helps when they add something new to solving the problem. So in some sense, they should be uncorrelated. They should be offering some new point of view or new strategy towards solving the problem. If you just increase the number of agents, but they all behave in the same way or they all offer the same points of view, you're not going to get additional problem solving capability out of that. See, so what's one very high level rule of thumb? And it is that if your tasks are small and low risk and very much within the cognitive capabilities of one strong model, you're better off with a single agent. On the other hand, when you have more complex tasks that need to be decomposed into smaller, more manageable tasks or tasks that require independent verification, that's when you should lean towards a more multi-agent architecture. So that was a quick look at this paper, which looks at how we should be picking multi-agent architectures for various problems, how we shouldn't always be defaulting to simply mimicking human organizational structures. I hope you found that useful. If you like content like this, consider subscribing, like the video, and I will see you next time. Thanks.